Hello students, my name is Shashank Shekhar. So today we will study about the preparation of some important inorganic compound that are related to D and F block. Okay, so let us first start with the preparation of potassium dichromate. So if I talk about the uses of potassium dichromate, then it is used in the leather industry and it is also used as an oxidant. Right, oxidant means it can oxidize something and it reduces itself. Okay. So, how are they prepared? So, dichromates are generally prepared from chromate. So, this is the chromate that we have. Okay, so not chromate means they are generally prepared from chromate, and these chromates are prepared from the fusion of chromite ore. Okay, so this is the chromite ore. So, when we fuse this chromite ore with sodium or potassium carbonate, then we get the chromate. Clear? So what are we saying here? That if we use this chromite, okay, chromite ore, so this is iron, say FeCr2O4, and just treat it with sodium or potassium carbonate in the presence of excess of air, then we will get chromate. Okay. So depending upon the thing that we have used, so if we have used potassium carbonate, then we will get potassium chromate, and if we have used sodium carbonate, then we will get sodium chromate. Okay, clear? Let us see this reaction. So you can see here that if you are treating it with sodium carbonate, our this chromite or with sodium carbonate in the presence of oxygen, then we are getting sodium chromate plus ferric oxide and CO2 gas. Now, this yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give a solution from which orange sodium chromate can be crystallized. So we do the crystallization. Okay. How do we crystallize them? So if we just filter it, if we just filter this solution and if we just filter it and add acidified sulfuric acid, then it will give a orange sodium dichromate solution. Now this can be crystallized to get NaCr2, Na2Cr2O7, that is sodium dichromate. But what are we preparing here? We are preparing here potassium dichromate. So how you will prepare potassium dichromate? So for that we use the solubility, okay, relative solubility. So basically sodium dichromate is more soluble than potassium dichromate. So if we just treat this sodium dichromate with KCl, then it gives us potassium dichromate and NaCl. Now, these are also orange in color. So orange crystal of potassium dichromate is crystalled out, and the chromate and the dichromate are inconvertible in aqueous solution depending upon pH. So what is the meaning of this? So you can see here that initially we have sodium chromate. Now if we just treat it with acid, so then we are turning it into sodium dichromate. What does it mean? It means that we can interchange by changing the pH. So if we are increasing the pH, we are getting sodium dichromate. So the reverse is also true, that if we just decrease the pH, then we will get sodium chromate. Clear? So this is the structure of potassium chromate and dichromate ion. Okay. So here we have a tetrahedral structure for chromate, simple tetrahedral structure. It is the say perfect tetrahedral. Now if I talk about the dichromate, then here we have a bridging oxygen, and on the either side we have the chromate. Okay, so one unit here and one unit here, and this both of these units are tetrahedral in shape. Got it? So this is what potassium dichromate. If I talk about this bond length, it is 179 picometer. And if I talk about this bond length, then it is 163 picometer. Means this bond is longer, this bridging bond is longer than this terminal bonds. And the angle between these is 126 degrees. So this is overall structure of dichromate ion. Clear? Next is, so if you just treat this chromate with H plus, now you are getting Cr2O7 2 minus, and just if you just treat it with base, then you will get CrO4 2 minus. So see how easily they can be converted from chromate to dichromate just by changing the pH here. Clear? Now the chromate ion is tetrahedral. Same thing is mentioned here. The chromate ion is tetrahedral. You've seen this where the dichromate ion consists of two tetrahedra. Okay, two tetrahedra means this and this. These are two tetrahedra on corner with CR bond of 126 degrees. Clear? Now the oxidation state of chromium in chromate and dichromate is same. This is very important that oxidation state is not changing here. So both chromate and dichromate, in both chromate and dichromate, the chromium is having the same oxidation state. So what will be the oxidation state? If you just look back at the here, then you can see there is a charge of 2 negative here. Now 7 to the 14, each oxygen will have a charge of -2. So 7 to the 14 and 14 and plus 2 minus is left, means overall charge is 2 minus. So if you just bring that -14 on that side, then it will give you 14 minus 2, that is 12. 12 divided by 2 plus 6. So here the chromium is in +6 oxidation state. What about this? So 4 to the 8, 8 minus 2, 6. Okay, so again +6. So both chromiums of chromate and dichromate are in the same oxidation state, which is +6. Now, if you just talk about the reduction potential of this, so it is approximately 1.33, which is positive. So in acidic solution, its oxidizing action can be represented as follows. So sodium and potassium dichromate are a strong oxidizing agent because they are in the higher oxidation state. So they can go to a lower oxidation state of +3, for example. So here you can see that we have +6 oxidation state, which is going to +3, means 2 CRs are accepting 6 electrons in a total, and we are going to 2 Cr3+. Now the sodium salt has a greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. So we have seen this point earlier that sodium salt is more soluble in water. For that reason, we use them as an oxidizing agent in organic chemistry. Now potassium dichromate is used as a primary standard in volumetric analysis, and this is the reaction that it undergoes. So the same reaction it undergoes when it is used as a primary standard in volumetric analysis. Now let us talk about some uses of this acidified potassium dichromate. Okay. So if you see here, then these are some half reactions that are given below. In first reaction, what is happening? I minus is going to I2. So I has an oxidation state of -1 because the charge on it is -1. It is going to I2, which is the elemental form. So there the oxidation state will be 0. Next is SN2 plus. So SN has a oxidation state of +2, but on the reactant side it is +4. Again it is getting what? Oxidized. Oh, it is getting oxidized. What about H2S? So H2S has a oxidation state, sulfur has oxidation state of -2 in the H2S. But on the right hand side, again the elemental form will have a 0 oxidation state. Therefore, from minus to 0, again oxidation. And at last we have iron, which is in +2 oxidation state, and it is again, you can say it is again leaving 1 electron. Each iron is leaving 1 electron, and we are getting Fe3+. Clear? So these are all the oxidation half reaction, and acidified potassium dichromate is oxidizing all of them. So this point I am making here is that that potassium dichromate is used as an oxidizing agent. So how it is used? It can be used to oxidize iodides to iodine, sulfides to sulfur, tin in the oxidation state to tin in the oxidation state +4, and similarly iron 2 plus to iron 3+. Clear? Okay. Now let us say we are writing one reaction. So we are taking the example of Fe2+, which is going to Fe3+. So what we have done here is we have simply added this and this last reaction. So we got this final equation in which we are what in which we are oxidizing Fe2 plus to Fe3 plus. Now you can similarly, what you can do is you can take this reaction and add to each of this individually. Then you will get a net reaction for this, a net reaction for this, and a net reaction for this. And in that process, your left hand reactant will be oxidized to the right hand product. Clear? So in this way, our potassium dichromate act as a oxidizing agent. Now let us talk about the preparation of potassium permanganate. So how it is prepared? So it is prepared by the fusion of MnO2 with an alkaline metal hydride. Okay. So how it is prepared? It is prepared by fusion of MnO2 with a alkaline metal hydroxide and oxidizing agent like KOH. Now this produces the dark color K2MnO4 which disproportionates in neutral or acidic solution to give permanganate. So first we have MnO2 here. Now in the presence of metallic hydroxide, or you can say any oxidizing agent, and in the presence of air it get oxidizes to K2MnO4 which is potassium. What? It is potassium manganate. Okay, potassium manganate. Now what will happen in the next step? This will get dissociated, or you can say disproportionated easily in the neutral or in the acidic solution. They have done this in the acidic solution to give what? To give what permanganate. Okay, you can see here that is going to permanganate and manganese oxide. Clear? Okay. So this is the reaction. First, it is fused with KOH to give MnO4 2 minus, and then again electrolytic oxidation of alkaline solution to give permanganate, to manganate to permanganate. Now commercially it is prepared in this way. If you talk about the laboratory method, then it is done with the help of peroxo disulfate, in which the peroxo disulfate is converting your Mn2 plus in the presence of H2O to MnO4 2 minus, that is permanganate. So we are taking a salt of what? We are taking a salt of manganese 2 plus, right? And on reacting it with peroxo disulfate, it gives permanganate. Clear? Okay. If I talk about the appearance of potassium permanganate, then it forms dark purple color. What does it form? It forms dark purple color crystal which are isostructural with KClO4. So if you remember the structure of KClO4, it is tetrahedral. Okay, it is tetrahedral. The same structure is adopted by the manganese O4 minus. Okay. Now the salt is not very soluble in water. If we talk about solubility, then in each 100 grams of water, we can only dissolve 6.4 grams of potassium permanganate. But when heated, it decomposes at 513 Kelvin. Okay, this thing decomposes at 513 Kelvin. Okay. It has two physical properties of considerable interest, and the first one is intense color, and second one is it is diamagnetic in nature. But this diamagnetism is changing along with temperature, and with temperature it can also show paramagnetism, right? So these are the two physical properties of what? Potassium permanganate. First is the intense color, and second is what? Second is changing of magnetic behavior under different temperature condition. So this is the structure of potassium permanganate. On the left side we have MnO4 2 minus, and on the right side we have MnO4 minus. Now you can see that they both are isostructural with ClO4 minus. So if you just place manganese in place of chlorine in place of Cl, then you will get ClO4 minus. So this is green in color, this is purple in color, and this is the structure of both permanganate and manganate. Now if I talk about this structure, so it can only be explained with the help of MOT, and which is beyond the scope of this this class. Okay, this class syllabus. Now, permanganate and manganate are tetrahedral. If I talk about the bonding, the pi bonding takes place by overlap of p orbital of oxygen atom with d orbital of manganese. So this is called synergic bonding. So this happens with carbonyl. We will see this in next chapter in the coordination compound, where we will see that there is a synergic bonding between the metal and the ligand. So they are metal are accepting, on the same time they are donating electrons also. So the green manganate is paramagnetic because of one paired unpaired electron, and the paramagnetic and the permanganate is dimagnetic due to the absence of unpaired electron. So the green one is what? Means the MnO4 2 minus is paramagnetic because it has one unpaired electron. Okay, but the MnO4 minus is dimagnetic because there is no unpaired electron. Now acidified permanganate solution oxidizes oxalate to carbon dioxide, iron 2 plus to iron 3 plus, nitrites to nitrates, iodides to free iodine. So here also we have the oxidizing property of the potassium permanganate similar to that of potassium dichromate. Okay, let us see those properties. So these are the three reactions. Okay, so in the first reaction we are going from Fe2 plus to Fe3 plus. This is the half reactions of the species getting oxidized. So in the first reaction, the iron 2 plus is getting oxidized to Fe3 plus. In the second reaction, nitrites is getting oxidized to nitrates. And the last reaction, the iodine is getting oxidized to iodide is getting oxidized to iodine. Now the full reaction can be written by adding the half reaction of KMnO4 to the half reaction or the reducing agent balancing wherever necessary. Representing the reduction of permanganate to manganate, manganese dioxide and manganese salt by a half reaction captures the process effectively. So what is said here is that the half reaction is this, means the oxidation half reaction is this, while the reduction half reaction will be reduction of permanganate to manganate, manganese dioxide and manganese. So this is the reaction. Okay. Now it is evident that hydrogen ion concentration of solution plays an important role in influencing the reaction. So in this reaction also we are seeing that by changing the pH we are changing the species. Okay, by changing the pH we are changing the species. And similar was the case for potassium dichromate also. And here also potassium permanganate is also behaving similarly. Now, although many reactions can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. So permanganate should oxidize water, but in practice the reaction is extremely slow. A few important reactions of KMnO4 are given below. So we'll study this. Here are the reactions. So what it is said here is that okay, the redox potential is enough to predict the reaction direction. Okay, but if I talk about practical sense, then this can be only useful if we know the rate of reaction also. So for example, the permanganate at H plus it should oxidize water. So this is clear from the redox potential. But if you just use this, but it goes very slowly, right? It goes very slowly, and due to this reason, we cannot use this reaction. Clear? We cannot use this reaction. Next are some reactions in different solution, in different pH of solution. So if I talk about acidic solution, then in the acidic solution, what happens? The potassium permanganate react with iodide to give iodine and Mn2 plus. Clear? Similarly, if we just treat our Fe2 plus with MnO4 minus, then Fe2 plus is oxidized to Fe3 plus. Similarly, our oxalate or oxalic acid is oxidized to what? Carbon dioxide at 333 Kelvin in the presence of MnO4 minus, and H2S is oxidized to sulfur. Clear? Now again, sulfurous acid, that is SO32 minus, in presence of KMnO4 minus, an acid, it gives 2Mn2 plus. Similarly, nitrite is oxidized to nitrate. If I talk about the neutral or the faintly alkaline solution, okay, if I talk about the neutral or the faintly alkaline solution, a notable reaction is the oxidation of iodide to iodate. So here iodide is getting converted into iodate. Okay, this is iodide. Sorry for this. It is iodide. It is getting converted to iodate. Similarly, thiosulfate is getting converted to what? Sulfate. So S2O3 2 minus is getting converted to sulfate in presence of MnO4 minus. And Mn2 plus is getting converted to what? MnO2. Manganese salt is oxidized to MnO2. Now, besides its use in analytical chemistry, potassium permanganate is used as a favorite oxidizing agent, right? In preparative organic chemistry. Okay. It is used for bleaching of wool, cotton, okay, and other textile fiber, and for the decolorization of oils also. So this is all about the preparation of potassium permanganate and potassium dichromate. So let us just revise all these reactions one more time from the start. So first of all, if I talk about the preparation of potassium dichromate, so first of all we use a chromite, chromite ore, that is FeCr2O4. Then in the next, what do? We take this and just treat, or you can say fuse it with the chromate, say sodium carbonate. This will give you what? Chromate ion. Okay, Na2CrO4. Now once we get Na2CrO4, then what do? We just treat it with H plus or change the pH. That would give us Na2Cr2O7. So sodium chromate to sodium dichromate. In the next step, what will happen? Since the sodium dichromate is more soluble, if you just treat it with KCl, it will give you potassium dichromate, which was our what? Which was our requirement. Now, orange crystals of potassium dichromate crystallize out. The chromate and dichromates are interconvertible in aqueous solution depending upon pH of the solution. So this is a very important point, that chromate and dichromate, what can be done? They can be interconverted if we just change the pH. So here is a demonstration of that. So this is the demonstration. If we are increasing the pH, then we are getting dichromate. If we are increasing the OH concentration, or you can say decreasing the H plus concentration, then we are getting chromate here. Okay. If you talk about the structure of chromate and dichromate, so chromate is tetrahedral, whereas dichromate has two tetrahedra with oxygen in between. Okay. And here the bond angle is 126 degrees, while the bridging CRO has a bond length of 179. The terminal one has a bond length of 163 picometer. So if we talk about the properties, so since it is used as an oxidizing agent, it has a lower reduction potential. So these are the reaction it can oxidize. Okay, if you just if you just add these reactions with this reaction, okay, each of these reaction individually with this reaction, then you will see, then what you will see? You will see then this all are getting oxidized. Okay. Okay. So here is the illustration of that. We have just added here one. You can just try the rest of 5, rest of 3 with the same reaction. You need to just balance at last. Now, if I talk about potassium permanganate, then how it is prepared? In potassium permanganate, first it is the potassium permanganate is prepared by the fusion of MnO2 with an alkali metal, that is KOH. So first we fuse it, then we get potassium manganate. Then in neutral or in acidic solution, this potassium manganate gets disproportionated into potassium permanganate and manganese dioxide. Now in industrial method, this is done with the help of electrolytic oxidation. So this disproportionation reaction is done with the help of electrolytic oxidation in alkaline medium. Now if we talk about the laboratory method, then we take manganese 2 plus iron salt and treat it with S2O 8 2 minus, right? Then we will get what? MnO4 minus potassium permanganate and sulfate ion. If I talk about the solubility, so it is very less soluble. That is, in each 100 gram of water, there is 6.4 grams, and the structure, as I have said you, it is isostructure with KClO4. So MnO4 minus and KClO4 are isostructural. Clear? So it has two physical attributes which is very much unique to this potassium permanganate. First is the intense dark purple color, and second is the variable magnetic property that is totally dependent upon temperature. So these are the two structures. This is the permanganate, which is green in color, where this is manganate, which is green in color. This is permanganate, which is violet in color or purple in color. Now, as I have told you earlier, that they show synergic bonding, means this metal is donating electron to this ligand. At the same time, this ligand is getting electrons to manganese. Okay, so both can be seen here. So through the sigma bond, the electron is donated, and through the pi bond, the electron is accepted. Now, if I talk about the oxidizing property, so the acidified permanganate can be used to oxidize these three. So iron 2 plus to iron 3 plus, okay, nitrite to nitrate, iodide to iodine. Now the full reaction can be written by adding the half reaction, as with the similar with the case of potassium dichromate. We have to add each of these reactions to give the final reaction. Clear? Now we can change the pH and change the MnO4 minus to various species. In the first one, we are changing permanganate to manganate if we are just oxidizing it, okay, so reducing it. If you are just increasing the pH, okay, if you are increasing the pH, then you will get MnO2, means manganese dioxide, and if you further increase the pH, then you will get Mn2 plus. Clear? And this is the potential for that reduction. Now we have said that this reaction are sometimes feasible, but the process is very slow. So the kinetic part is also very important. Like the permanganate at at a concentration of H plus is equals to 1 should oxidize water, but in practice this happens very, very, very slowly, right? Now let us see where the behavior of this potassium permanganate. We have seen this. We are revising it. At an acidic solution, it oxidizes H plus to H2O. Okay. And for Fe2 plus, it is getting oxidized to Fe3 plus. Similarly, the oxalic or oxalate ion is getting converted to carbon dioxide, and S2 minus is getting converted to sulfur. Whereas this sulfurous acid is getting converted to sulfate, and nitrite is getting converted to nitrate. If you talk about the neutral solution, then in neutral solution, iodide is converting to iodate, whereas this thiosulfate is getting converted to sulfate, and at last Mn2 plus, that is manganese salt, is converted into MnO2, that is manganese dioxide. So this was for today's lecture. With this, I end my lecture. Thank you.